Hi, welcome to my video. This is a brief presentation of this stock paper, Self-Improvement for Circuit Analysis Problems. The general idea is we want to understand for particular types of problems, when can you use algorithms for the problem to get even better algorithms for the problem, like somehow based on maybe the structure of the algorithm or the structure of the problem itself. So the general motivation is we have an algorithm A for a problem X running in time T, and we want to know under what circumstances do we have an algorithm A prime for a problem X, or maybe a slightly different problem X prime that runs faster in time, some T prime, which is much less than T. Okay, so just to give some idea of like what on earth could this mean, we know examples where this sort of thing is not possible. So canonical example is the time hierarchy theorem, that time t is properly contained in time t to the 1 plus epsilon. And in general, this says you can't simulate an arbitrary algorithm on an arbitrary input much faster than just a step-by-step simulation. Okay, because if you could, then you could predict in advance what the algorithm is going to do and do the opposite, right? The standard diagonalization argument. And this sort of shows, I guess, intuitively that certain forms of self-improvement can't exist. So there's also like a famous implication that, like, say, if you've got time into the 1 plus epsilon, you could simulate it slightly faster in linear time. You could apply this inclusion to itself and show that time into the 1 plus epsilon squared is contained in time into the 1 plus epsilon, which is contained in linear time. Time into the 1 plus epsilon cubed is in linear time, and show that all of P is in linear time, right? So this can be used to show tight time hierarchy theorems, even if you have, even in computational models where you have some arbitrary polynomial overhead in your simulation. So this is more about like impossibility of self-improvement, just to give you some idea of what I'm trying to get at. But another motivation for this work, it comes from thinking about some hypotheses in fine-grained complexity. So in fine-grained complexity, there are two major hypotheses about the SAT problem beyond just assuming P is in from NP. There's the exponential time hypothesis of Pagliazzo, Paturi, and Zane from 01 that shows that, well, it claims that there exists an epsilon, so that 3 SAT is not in 2 to the epsilon n time. Okay, now we know that 3 SAT has some slightly faster algorithm, about 1.08-ish. But the hypothesis is that you can't just arbitrarily improve the space of the exponent to something much like arbitrarily close to 1. So you can think of it as saying 3 SAT is not in 1.00001 to the n time for some number of zeros. Okay, there is some point at which you aren't going to be able to make this basic exponent arbitrarily close to 1. So this is a weak exponent lower bound, where we have a t of n time algorithm, like 2 to the n time, or even 1.308 to the n time. We want to argue that there's some delta so that we can't have a t of n to the delta time lower bound. Okay, that's some sort of weak exponent lower bound, saying there is some kind of exponential behavior, but we don't know exactly what the base of the exponent is, and we don't care. Okay, so in a more fine-grained setting, there's the strong exponential time hypothesis, which states that for every epsilon you choose, so no matter what epsilon you choose, so 2 to the 1 minus epsilon that you choose, there is some clause with k so that k SAT is not in 2 to the 1 minus epsilon n time. Okay, I mean, another way of saying this, not quite the equivalent, but morally equivalent, is that the CNF SAT problem with no bound on the clause width is not in 1.9999999 in time for every string of nines you could think of. So for arbitrary clause width, the base of the exponent 2 is the right answer. Okay, and so we think that this is a strong exponent lower bound. saying we have a time T of an algorithm for the problem, and we want to argue that you actually just can't improve this to T of n to 1 minus epsilon for any epsilon. Okay, so this T of n is really as best you can do. Okay, so these are sort of the two major hypotheses about SAT. And it's known that this strong exponential time hypothesis implies tight lower bounds for many problems in P, many, okay. Don't even have space to get started with the references for that. And it is known that the strong exponential time hypothesis does imply the exponential time hypothesis is actually stronger. This, at a high level, uses the so-called sparsification lemma that says for an arbitrary k-set instance, there's a sub-exponential time reduction that will reduce the k-set instance to instances that have only a linear number of clauses, linear number of variables. Okay. The big question here that I want to talk about is whether ETH implies strong ETH. Okay. Could it be that this weak exponent lower bound implies a strong exponent lower bound? Right? Another way of thinking about it is thinking about the contrapositive. Could we show that if SAT is in 1.999 to the n time, could we improve this algorithm, maybe using the algorithm itself to show that SAT is in 1.0001 to the n time for any number of zeros, right? So this is basically like showing that the negation of strong ETH implies a negation of ETH. Okay, so this would be some sort of like some bootstrapping argument for the SAT problem. But given some algorithm that barely beats exhaustive search, you get something that decisively beats exhaustive search. Okay, so in the paper, we show how a weak exponent lower bound implies a type of strong exponent lower bound. Okay, so we certainly don't prove the negation of strong ETH implies negation of ETH. We prove something interesting along these lines. Okay, but your interpretation may vary, and you can look at the paper for alternative interpretations. So try to tell the reader all the different ways you can think about the results in this paper. But the starting point is a simple polynomial time solvable problem. Okay, so we basically set up the circuit SAT problem, which is NP complete, in a form which is solvable in polynomial time. And the idea is we give you a very large circuit in a very small number of inputs, and we just ask whether this kind of circuit is satisfiable. So given some parameter epsilon, we define epsilon large circuit SAT to be the following problem. I give you a circuit of capital N size, think of N as something big, with only epsilon log n inputs. Okay, so the number of inputs is very small. We want to know whether this circuit is satisfiable. Okay. Now, the usual circuit SAT problem is NP hard, but this problem is certainly not NP hard. I mean, we made the circuit so large that brute force is going to be polynomial time, right? So brute force will take about n to the 1 plus epsilon time. Okay, and it's just trying all the possible settings of the inputs and just evaluating the circuit. We want to know whether this is an optimal algorithm. So we have some polynomial time version of the SAT problem. We want to know we have a nearly linear time algorithm. Think of epsilon as being arbitrarily small. We want to know, is there a faster algorithm than that? Okay. So the first theorem that we prove, or at least one way of stating the theorem in the paper, is that if there exists a single epsilon, so that this epsilon large circuit SAT problem is an n to the 1 plus little of 1 time. Okay, so we go from n to the 1 plus epsilon time to n to the 1 plus little of 1 time for some tiny epsilon. Doesn't matter how small it is, some epsilon. Then, given this, we can say for all epsilon, circuit SAT on sub-exponential size circuits is n to the epsilon n time. Okay, so we go from a problem which is in polynomial time, nearly linear. If we may improve this polynomial running time from n to the 1 plus epsilon to n to the 1 plus little of 1, Then we get an arbitrary polynomial improvement for the circuit set problem on sub-exponential size circuits. So we reduce the input size, right, to our circuit set problem. It becomes harder because brute force search is like sort of further away from polynomial. And this would take to the n times to the low of n time in the worst case, and we get an arbitrary polynomial improvement here. Okay, so this sort of consequence would imply the negation of ETH. In fact, the negation of a circuit form of ETH, not just 3-sat, but the circuit set problem itself can be solved in sub-exponential time. And this is so powerful that we can even show structural complexity results like, okay, if this consequence is true, this consequence would imply n time of t is in the intersection over all epsilon of time to the epsilon t. Okay. Yeah, so this would be sort of a major consequence for simulation non-determinism from what seems to be something innocuous, like taking a polynomial time algorithm and running it slightly faster. Okay. So what's crucial in these arguments is we need an algorithmic model where t time converts nicely to t to the 1 plus the 1 size. It's just a technical caveat. So when I talk about time here, I mean something like a multi-tape Turing machine model. However, this argument method is so general that we could put size here and size here, and everything is just fine. But the thing is, what's going on is you're going to take an algorithm for circuit set, you're going to make a circuit out of it, and call that on another algorithm. There's sort of a lot of algorithms being called on other algorithms here. So this caveat here applies, but it's not a big deal. There's lots of other versions that one can prove with this general argument. And indeed, more general statements can be made. So for example, we can say, suppose for all alpha and beta, where alpha is at most beta, circuit sat on n inputs into the alpha n size is into the beta n time. Then if that's true, then circuit sat on sub-exponential size is into the beta minus alpha n plus little n time. Okay, so you tell me, the size in which you can get, a better circuit set algorithm, and I will tell you a better algorithm you can get for the sub-exponential size circuit set version, right? So just to think about this, when beta is equal to 1 plus alpha, there's no improvement. That's basically like exhaustive search over all possible to the n choices. When beta is alpha plus delta, we get to the delta n time for too little n size. Okay, and so this theorem 2 implies the theorem 1. All right, and in fact, we can show something much stronger, like basically some kind of interesting equivalence where an existential quantifier can replace the universal. So let me tell you one form of stating this. So the third theorem I want to mention is that the following are equivalent. So the first bullet is that there is some epsilon. So this epsilon large circuit set problem where we have epsilon log n inputs and n size is in into the 1 plus little 1 time. So this was like the hypothesis in our theorem 1. This is equivalent to the statement that for all constants C, all constants, including like 100, a billion, whatever, C large circuit set is also in the 1 plus little 1 time. So you can have like a billion log n and n size would still be in nearly linear time. Okay, so like the naive algorithm for this problem in bullet 2, would be n to the c times n roughly. So n to the c plus 1. And so from this sort of tiny polynomial improvement we get, like improving n to the 1 plus epsilon to n to the 1 plus little 1, we could get something which is an arbitrary polynomial improvement for the same type of problem. Okay, so that's the second bullet. And the third bullet shows we can go even further. We can take a sort of alternating versions, like versions in the polynomial hierarchy of circuit set, and improve them as well. So for every constant c and for every constant k, sigma k, where we get existential variables for all variables, existential variables, universal variables, and we have like k blocks of these. So the SAT problem for that would also get an improved algorithm. Okay, and so all of these are equivalent. So starting from this sort of innocuous looking thing, you can get algorithms which look much, much stronger for circuit analysis problems. Okay. Okay. So like this green box here implies very interesting consequences, contradictions to ETH for even like problems in the polynomial hierarchy. Okay. And there's many other extensions and variations that I'd like to mention. You can look at the sharp circuit set problem where we're given a circuit C. We want to output the number of satisfying assignments. And there's an analogous theorem 2' to the theorem 2 that we stated before, where if you have a sharp circuit set algorithm for a particular size running in a particular time, you can get an improved algorithm for subexponential size circuits. Okay, so everything that I said before for circuit set applies equally well to the counting version of circuit set. But not only that, we can get similar theorems for the quantified version of circuit set, where you have arbitrary quantifiers on your Boolean variables. You exist for all, along with a circuit predicate at the end. And you want to know whether the overall like quantified sentence is a true or a false sentence. And so this is a famous p-space complete problem. And there's a completely analogous theorem for the quantified circuit set as well, like this sort of self-improvement statement. And all the above hold for like if we put size S circuits in place of time S algorithms. So there's non-uniform versions of these results. And also for randomized models, if I have randomized circuits or randomized algorithms, that like for this epsilon large circuit set, I get all the same nice consequences for randomized circuit set, for sharp circuit set, for quantified circuit set, right? And we can actually use the arguments for a sharp circuit set to prove new uniform circuit lower bounds. Okay, so just to give an example of what we can show in the paper, the circuit evaluation problem, which is solvable in quasi-linear time, nearly linear time. So I give you a circuit, I give you an input. I want to know what the output of the circuit is on this input, okay? So that's the problem. And we think of the circuit as having a single output. This is a decision problem. This very simple quasi-linear time problem, we can prove a depth 2 circuit lower bound for it with arbitrary symmetric gates. So sim of sim means there's an arbitrary symmetric Boolean function there. So we can show that this circuit problem doesn't have sufficiently uniform polylog time uniform. It just means that there's a very efficient way of printing gate information about these depth 2 circuits. Circuit evaluation doesn't have circuits this form with into the 1.19 gates. Okay. What's interesting here is that these kind of uniform circuit lower bounds that have been proven in the past, they work by some indirect diagonalization. And then you needed like a problem that was sort of strong enough, like this. You needed the SAT problem here, or maybe like something in a polynomial hierarchy, or maybe like sharp SAT or something like that. Whereas here we can actually prove such a lower bound against a problem in quasi-linear time. And so that's what's sort of novel about this kind of uniform lower bound. And these sim of sim, so arbitrary symmetric Boolean function of arbitrary symmetric Boolean functions, just some extremely annoying circuit class that shouldn't be very powerful, but it's very difficult to prove things about it. Oh, and this theorem somehow uses fast rectangular matrix mult, like the algorithm in it, in order to get, so the rectangular matrix mult exponent is somehow related to this 1.19 in some interesting way. If you like matrix mult, just, there you go. You see the paper for more details. So I want to also mention there is an FPT version of this result. So, and this is maybe the most striking form of self-improvement. So it really does show that, you know, getting some algorithm for circuit set of a particular form of running time implies an algorithm for circuit set with a strictly better form of running time, or strictly better looking form of running time. So the theorem we can prove is, suppose there exists a constant c greater than 1, okay? So that for all epsilon, the circuit set problem has circuits of size c to the k plus n to the 1 plus epsilon, okay? Right, so if we think of circuit set as having k inputs and n size, then we get in a 2 to the k times n to the 1 plus little 1 time, and we want to know whether you can get something faster. Can we take this product between 2 to the k and 1 plus little 1 and make it a sum? Right, suppose there exists some constant, maybe it's, you know, enormous constant, like I don't know, 10 to the 10 to the 10 to the 10. All right, so we can put 10 to 10 to 10 here to the k plus something that depends nearly linear on the circuit size. If that's true, then for every constant c greater than 1, so we can make this constant c arbitrarily close to 1, circuit set will have circuits of size this arbitrarily tiny constant close to 1 to the k plus n to the 1 plus low 1 time. And we can also put an epsilon here for all epsilon and the 1 plus epsilon time. So this is saying an equivalence between some existentially quantified statement about circuit set and some universally quantified statement. If you can just find like some extremely enormous constant so that circuit set has circuits of size extremely enormous constant k plus some nearly linear thing, then in fact we can contradict ETH. Okay, so, and we can make this constant c arbitrarily small, arbitrarily close to 1. Okay, and okay, so just an interesting fact is that if we reverse the quantifiers in the statement above, it's actually true. Okay, and you can maybe pause the video and look at these inequalities to see why. Is this one of some kind of parameter manipulation to get a running time of this form? So it's just like, okay, if we just reverse the order of these quantifiers, then ETH is false. Okay. I think I'm out of time. I think maybe hopefully I've advertised enough of this paper so you're super hyped and interested and ready to go look at it and read it and look at the open problems and prove something for me. Okay, thanks very much for your time. Thanks for watching.